Good day, everyone, and welcome to Group 3 presentation. We were given the student performance dataset, and we created a statistical analysis of the factors influencing students' academic performance by identifying the key drivers for success and failure in high school education. With this, our goal is to determine what actually drives academic performance, whether it be demographics, habits, or support systems. To identify that, we broke it up into three questions. The main one being, what factors are most significant predictors of a student's GPA? Then, are there statistically significant differences between student groups? And the prediction, can we accurately predict a student's final grade class using statistical method? The dataset given contains 2,392 records and contains a range of academic, demographic, and behavioral variables used to understand student performance. Descriptive statistics were used for three main reasons. One, to understand the data distribution. Measures such as mean, mode, and median, and standard deviation help identify whether data is centered or skewed or contains any outliers. Secondly, it was done to establish a foundation for analysis. Before performing ANOVA or regression, it is necessary to evaluate whether variables behave normally, show large variance, or contain any outliers. And lastly, to summarize key patterns for interpretation. Variables like GPA, student study time, and absences are essential indicators for student performance. This helps highlight general trends in data. For example, whether a student typically study a lot or have high absent records. Based on our analysis, the GPA majority range between 0 and 3, meaning mostly C and D grades, and the study time is an average of 9.8 hours per week. Absences have an average of 14.5 days missed. Now looking at our output on the right, we can see that the GPA distribution. This means that most students cluster between 1.5 and 2.5, which corresponds roughly to C and D grade range. The tail on the right side indicates that fewer students are achieving GPAs above 3.0. This suggests overall academic performance in this population is relatively low, with a small population of high-performing students. Next, we move on to the study time distribution. In the second graph, we see the distribution of the weekly study time. The average is 9.8 hours per week, but the distribution has a wide spread showing that students' study habits vary. Interestingly enough, the mode for this is much higher, around 20 hours, which suggests that while the average students study less than 10 hours, there are a large subgroup of students who study significantly more. And lastly, the absent distribution. The third graph shows the distribution of the student absences. The mean number of absences is 14.5 days, as mentioned before, and it is right skewed. There is a noticeable peak at 25 absences, which matches the calculation mode. This means a surprisingly large number of students miss long periods of school. We ask ourselves, can this pattern be linked to a lower academic performance? Now with further analysis, we see the exact amount for the GPA, mean, median, and mode, and standard deviation. The mean and median are almost identical, which normally indicates a fairly symmetrical distribution. The GPA distribution has a high standard deviation, meaning academic performance vary widely between students. This means a large portion of students is struggling academically. Next, we move on to the study time weekly, with the following output as seen. The average study time is about 10 hours per week. The mean and mode is relatively close. However, the mode is nearly 20 hours, which doubled the average. This means that there is a large subgroup of students, even though a typical student study much less. This means that the distribution is rightly skewed. Next, we move on to the absence, with the output as seen. The students miss on average 14.5 days or 15 days of the school week. The mode is 25 days, meaning a large group of students miss a lot. The high standard deviation shows wide differences in attendance patterns. The attendance are heavily right-skewed and driven by a group of students with extremely high absence. Poor absence can be a significant factor that negatively affect the student grade class. This will be further examined later on.
We also conducted a probability analysis which revealed that the succession of a student's academic performance leans more behavioral than demographic. Using 3.0 as a high GPA on a 4.0 scale, we found that the probability of a student that has a high GPA and is female is 6.73%, and the probability that a student that has a high GPA and is male is 6.69%. 0.04% is not a statistically significant difference to conclude that a student's gender influences their academic performance. We then moved on to the study time and used the median split to define the lower and higher time a student spent studying. We then tested the probability of a student that has a high GPA and has a higher study time to be 17.3%. It can be concluded that a student who studies more are more likely to achieve a high GPA, outperforming the overall high GPA rate, which is 13.4%. Again, using median split to define high and low absences, we tested the probability of a student with a high GPA and has low absences, which is found to be 27.1%. Low absences appears to be one of the strongest predictors of the strong academic outcomes. Students with a good attendance are twice as likely to achieve a high GPA compared to the general population. We also explored the analysis of extracurriculars on a student's academic performance and found that the probability of a student with a high GPA and also participates in activities like sports, music, or volunteering to be approximately 5%. Hence, these activities has no significant impact, and it can be concluded that extracurriculars neither hurts nor helps a student's grades significantly.
So in our methodology, we checked whether GPA data followed a normal distribution, which is an important requirement before running any statistical tests. To do this, we use both the QQ plot and the Shapiro-Wilks test. And the Shapiro-Wilks test results showed where W was 0.98, the p-value was less than 0.001. And because the p-value was very small, it tells us that the GPA data is not perfectly normal. And when we look at the QQ plot, the data deviated from the normal distribution, particularly in the tails. So although the center of the distribution is roughly normal, so the curvature in the tails confirm that the data is not perfectly, the data do not perfectly satisfy normal distribution. And when we looked also at the Welch t-test, because of the large data set, we proceeded with the parametric analysis such as the t-test and the ANOVA, right, which also indicated statistically significant difference in GPA scores between tutored and non-tutored. And when we look even at the confidence interval for the differences in means was minus 0.37 to minus 0.210, which does not include 0. And this also confirms that tutoring is associated with higher GPA. So we analyzed the role of parental support in influencing student GPA using one-way ANOVA. Our goal was to determine whether GPA differs across the 5 levels of parental support. we established the null hypothesis that all groups have the same mean GPA, while the alternative hypothesis states that at least one group differs. So the chart on the left side illustrates the F distribution and the critical region. The dashed line represents the critical F value of about 2.38. Our actual observed F statistic was 22.72, which is shown far to the right of the critical value chart. This places it deep within the rejection region, indicating strong evidence against the null hypothesis. This, even the corresponding p-value is less than 0.001, which further confirms that result. So the ANOVA result summarizes this finding. Overall, our analysis shows that GPA varies significantly across parental support categories. Students who receive higher levels of parental support tend to achieve notably higher GPA.
To summarize the relationships between continuous variables, we generated this Pearson correlation heat map. And as we can see on the diagram there, we see two strong correlations between GPA and study time, as well as absences. The coefficient for absences is negative 0.92, and this tells us that as the absences go up, GPA goes down in almost a straight line. In contrast, study time, which is a light blue square, shows us that it has a positive correlation with GPA of 0.18, and it helps, but not as much as how absences negatively affect GPA. So the takeaway is that you simply cannot outstudy chronic absenteeism. Now having understood the mean relationships of the dataset, we built a multiple linear regression model which aimed to predict GPA. So the model from included variables like study time, absences, and support. The results were pretty strong, and it showed an adjusted R-squared value of 0.954, and with a p-value very close to 0, making it highly statistically significant. And the R-squared value means that our model explains 95.4% of the variation in student grades. And this is also consistent with our correlation matrix, as absences were the dominant factor with a negative correlation, and demographic factors such as age and ethnicity were not statistically significant as shown previously. Even though the R-squared value was very promising, we needed to check for collinearity to make sure the model was reliable and if predictors were correlated with each other. So to do this, we calculated the variance inflation factor, VIF, as seen on the table there. And all values were very close to 1, and a value usually below 5 is typically acceptable. So ours is very clear that indicators that the coefficients are reliable and independent. So we showed that the model was not collinear. Next, we validated the model assumptions visually. So the first one we look at was homoscedasticity, and that's basically if the variance is equal, which was one of the key assumptions. And the residuals versus fitted plot to the top left, it showed that a flat red line, meaning that the variance error was consistent across the range. So it did follow that assumption. Secondly, we tested for normality, and the QQ plot to the top right of residuals hug the diagonal line closely, so this confirms that the errors were normally distributed. Thirdly, we tested for outliers, and the residuals versus leverage plot to the bottom right showed no point outside of Cook's distance, so it met the assumption. And the model, therefore, is very statistically sound and meets all of the assumptions as shown. So to summarize our presentation, we so far observed that habits outweigh the demographics of the student. However, we must look at this critically. When dealing with complex human behaviors such as this, finding a correlation of negative 0.92 when R-squared of 95% is suspiciously rare. And a study showed that by Swiderski show that absenteeism is usually between 0.05 and 0.057. So not as statistically so significant as we found. And this leads us to suspect that the dataset might be synthetic or mathematically derived. While the statistical relationship holds in a real world scenario, we would expect much more noise it puts in the dataset. And actionable insights shows us that intervention should focus on attendance and parental support, which yielded the biggest ROI for students' GPA. To conclude, our analysis discovered three clear takeaways from the dataset. Number one is attendance is non-negotiable, as it is the strongest predictor of GPA. Two, support systems work. Interventions via parents and tutors yield a statistically significant ROI. And three, effort matters. Strong work ethic and consistent study time is positive, but it relies on attendance as a foundation. In closing, thank you for listening, and we are now open for any question regarding our findings.